Hey everyone, welcome back to my YouTube channel Act 1. The anomaly. Look up at the night sky. There it is, our constant companion, the moon. For billions of people across millennia, it has been a source of wonder, a beacon in the darkness, and a symbol woven into the very fabric of human culture. It controls our tides, illuminates our nights, and has inspired poets, lovers, and scientists alike. For all its familiarity, the moon harbors a profound secret, a cosmic enigma that challenged our understanding of planetary formation for centuries. It is not just a rock in orbit. It is a monumental puzzle piece in the story of Earth itself, a story that begins with an unthinkable catastrophe, a collision of worlds. Our moon is an anomaly in the solar system. Consider its sheer size. It is massive, roughly 1/4 the diameter of Earth, making it the largest moon relative to its parent planet among all the major planets. Jupiter's Ganymede is larger in absolute terms, but Jupiter is truly colossal. Our moon's substantial size has profound implications, stabilizing Earth's axial tilt and contributing to the very conditions that allowed complex life to flourish. But where did such a behemoth come from? This question has plagued astronomers for generations. Early theories struggled to explain its existence. Was it captured by Earth's gravity, a rogue asteroid pulled into an elaborate dance? Its orbit is too stable, too circular, and its composition too similar to Earth's for a simple capture scenario to hold. Did it form alongside Earth from the same primordial cloud of gas and dust, a sister planet in miniature? If so, why is it so different in density, lacking the dense iron core that defines our own world? The moon's average density is significantly lower than Earth's, hinting at a depletion of heavy elements. And then there's its orbit, slightly tilted relative to Earth's equator, a subtle but significant detail that defied easy explanation by co-accretion models. The mystery deepened with the arrival of the space age. And humanity finally reached out and touched the moon, bringing back precious lunar samples. The scientific community expected answers. What they found, however, only amplified the anomaly, pointing towards an origin story far more dramatic, far more violent than anyone had previously imagined. The evidence began to mount, suggesting that our serene lunar companion was born from chaos, from a cataclysmic impact that reshaped both Earth and its nascent satellite. Imagine a young Earth, barely formed, still molten, a tumultuous world hurtling through the early solar system. And then, imagine another body, a protoplanet perhaps the size of Mars, on a collision course. This is the stage for our story, the dramatic opening act of the giant impact hypothesis. This hypothetical impactor has a name, one given to it by scientists, Theia. Named after the Greek titaness who was the mother of Selene, the moon goddess, Theia is Earth's lost twin. A celestial body that, according to the leading theory, no longer exists, having been consumed and utterly transformed in a cosmic smash-up of epic proportions. The moon, then, would be the enduring scar, the magnificent child of that ancient, violent union. But how did we come to believe such an extraordinary tale? The clues, as always, were in the rocks. Act 2. First clues. Asterisk. For centuries, before the advent of space travel, theories about the moon's origin were largely speculative. One popular idea, championed by George Darwin, son of Charles Darwin, was the fission theory. This proposed that the rapidly spinning, molten Earth somehow flung off a piece of itself, a blob of material that eventually coalesced to form the moon. The Pacific Ocean basin was even suggested as the scar left behind by this dramatic separation. It was a romantic notion, but it struggled with the physics. Earth simply couldn't have spun fast enough to eject such a large mass, and the mechanics of how it would then stabilize into orbit were problematic. Another contender was the co-accretion theory, which suggested that the Earth and moon formed together, side by side, from the same swirling disk of gas and dust that gave birth to the rest of the solar system. It seemed plausible for many planetary systems, but it failed to explain the moon's distinct lack of a substantial iron core compared to Earth, nor its orbital inclination. If they formed together, they should have more similar compositions and orbits aligned with Earth's equator. Then there was the capture theory. Perhaps the moon formed elsewhere in the solar system and was later snared by Earth's gravitational pull as it passed by. While capture is a known phenomenon for some smaller, irregularly shaped moons of gas giants, capturing an object as large as our moon into such a stable, nearly circular orbit without either body being destroyed or flung away is an incredibly difficult feat, requiring highly improbable orbital mechanics. The true breakthrough came not from theoretical musings, but from tangible evidence brought back from another world. The Apollo missions, beginning in 1969, were a scientific goldmine. Astronauts collected hundreds of kilograms of lunar rocks and soil, samples that represented billions of years of the moon's history. When these precious samples were meticulously analyzed in laboratories back on Earth, they provided the first definitive clues that would unravel the moon's origin story. One of the most striking findings was the moon's extreme dryness. Lunar rocks were almost entirely depleted of volatile elements, substances like water, sodium, potassium, and zinc, elements that would typically be present in a body formed directly from the primordial solar nebula. This depletion suggested that the moon had experienced intense heating, high enough to vaporize and drive off these lighter elements. It pointed towards a fiery, high-energy formation event. Even more critical were the isotopic similarities between Earth and Moon. Isotopes are atoms of the same element with different numbers of neutrons. The ratios of various isotopes, particularly oxygen isotopes, act like a cosmic fingerprint, revealing the birthplace of a celestial body. Scientists expected that if the moon formed from a different body or was